Thank you. It's very hot today, very much like summer, but officially we already stepped into winter 2 weeks ago. Anyway, so I hope the AC is cool enough to get you through this talk. I'm Chang, a visiting scholar here. So I guess most of you cannot get a clue from the title to tell about what I'm going to tell you later. So I changed it to a more official title, which is Asteroid Interior Structure, a Perspective from Asteroid Rotation. I have many co-workers, and here I have Yingtong, Xiangyu, and Matt. And in NCU, I have Xinwen, although he already moved to University of Michigan. And my previous student Ting Suo, and of course Professor Win Ip and Wenping Chen, and also Fumi Yoshida from Japan. And I got data from many wide field telescopes, so here I list many of the teams which have provided me a lot of valuable data set. So I'm very grateful for their help. So here is the outline. I will give you some idea of how and why we want to study asteroid, and then what is their interior structure, and how I can use rotation period to learn their interior structure, and what do we learn so far, and how can we do further. And in the end, I will give you a summary. So this is simple picture of our solar system, except for the sun in the center. We have 8 planets, and then in the majority of the space, we have different kind of asteroid, which is show like the white dot here and here. And there are 2 major groups. One is between Mars and Jupiter, which is known as main belt. And then another majority is beyond Neptune, which we usually call them TNO, transient Neptunian object. And also we have some near Earth object, which means their orbit can intersect with Earth's orbit, and sometimes they will bring us some damage. And another big group is around Jupiter, which is co-orbiting with the Jupiter. They share the similar orbit, but in 60 degrees ahead and behind the Jupiter. This group is very interesting because we believe they share similar or the same origin of TNO. So study them can tell us some important information about the solar system formation. So we usually call small solar system body as the relics of solar system. So how do we learn asteroid? Well, we first have to identify where they are, which means we need to know their orbit, which is their dynamics. And then we will try to see how many are they, which means the population of each group. And what is the size distribution? Are they similar to each other, or they have some different, and how so? And then we would like to know what they are, which means what is the composition of that asteroid. And we can tell this from their color or spectrum. And after we obtain the information of this quantity, we try to correlate this quantity and try to do the archaeology of this small body, and as well the solar system. However, there is an other important property we would like to know, which is the interior structure, or we can say the bulk density. It's very important, but it's very difficult to obtain this information. So far, we don't have the direct measurement for any asteroid or for any moving object for their interior structure. Although Rosetta tried to censor the surface of Cummins 67P. However, because of the Philly landing fail, so we lose the chance. So we hope in the future we'll have a chance to direct measure the interior structure of asteroid. Why is interior structure is important? Because we believe it's less involved, which means it preserves more primitive information in the early stage. So it's a very straightforward quantity to be compared between different asteroid or moving object group. It's also very useful. As we know, some gift just falling from heaven, but it turned out to be a disaster. So sometimes you need to know how to deal with if an asteroid fall into or try to attack Earth. So interior structure is a very important information to do that, and also the idea of space mining and exploration. So what do we know about the structure of asteroid? We believe they have a structure called rubble-pile. So what is rubble-pile? It's just like this picture shows, a bunch of small pieces staying together only by their own gravity. So the key point is they only have gravity to pull them together. So the structure is very loose, which means it's very weak. And we believe at least asteroid larger than few hundred meters in this kind of structure. So how do we get this idea? From the space image, we saw a lot of boulders, so like this one, a lot of boulders just on the surface of the asteroid. This is the echo tower. So beneath the surface, we believe it also has such kind of construction from boulder. And also we observe many asteroid family in the main belt. Because we believe what is the asteroid family, which means a bunch of asteroids, they share some correlation in their orbit. So as you see, there are different colors, show you different asteroid group. And we believe this kind of asteroid family is produced from a parent body. If the parent body has strong structure like a rock, you need a lot of energies to destroy them. And eventually the small pieces created from the collision will gain a lot of energy, and eventually they will disperse and no longer dynamically correlated to each other. So if we see this kind of asteroid family, we believe they have a parent body which has a weak structure. Then you don't have to smash them so hard. And in this way, we can keep those small pieces dynamically correlated to each other. And so we see asteroid family. And also, we believe there are some porosity in asteroids. So when you compare the bulk density to their compositional material, you always see that the bulk density is smaller than compositional material, which means there are some empty space in the asteroid. So this is another evidence to support rubble-pile structure. And moreover, when an asteroid falls into the atmosphere, or they are too close to a planet, you will find them easily to be destroyed or torn apart. So which means their structure is very weak. So how do we have rubble-pile? In the main belt, because we have so many asteroids, they eventually went through a lot of collisions. So some collision is catastrophic, which means the entire asteroid can be destroyed, like this cartoon showed you. And then it breaks into many small pieces, and in somehow they find a way to reaccumulate back to each other, become a new asteroid, and form the rubble-pile structure. If the asteroid do not went through the catastrophic collision, they still have many minor collisions. So when you try to knock a rock, use hammer so many times, the rock eventually will have so many cracks inside their body. So this is another way to create rubble-pile structure. So as I say, they only have gravity to pull the small pieces together, so they cannot rotate very fast. Otherwise, the centrifugal force will overcome the gravity and then break the asteroid apart. So when you balance the gravity and centrifugal force, you eventually get this equation. It tells you that there is an up limit corresponding to the bulk density of asteroid. So if I do a survey for a group of asteroids and I try to identify a spin rate limit, then in turn it will tell you something about their bulk density. Okay, so before I step into how we identify the spin rate, we first to know how we measure the rotation period of asteroid. So here is an artificial asteroid which is elongated. As we know, asteroid won't emit optical light by himself. So we can see them is because they reflect sunlight. So when the area is bigger, the asteroid look brighter. If the asteroid is elongated and rotating, you will see the reflecting sunlight area is changed along with time. When it's bigger, it's brighter, smaller, dimmer, bigger, brighter. So it goes up and down, up and down. So when we collect a line curve, we try to see this repeat periodical pattern to identify their rotation period. Moreover, the amplitude in the line curve it somehow tell you the how elongated the asteroid is. So after we obtain a line curve, so for example, here is a line curve of 4 days for a certain asteroid. Then we fit the line curve to a second order Fourier series. You can try any method you want, but second order Fourier series is the traditional method. We try to find the rotation period of asteroid. Then it gives you a periodogram, and we identify the best fit frequency. Remember, we need to have a double dip or double peak line curve, facet line curve. That means a full period. Because if you just have one dip, one peak, it just will rotate halfway, not a full rotation. So who first to correlate the rotation period to rubble-pile structure? It was Alan Harris. He wrote a 2-page paper in 1996. And on the paper, it only shows this diagram. So here is diameter, here is the rotation period. And it used around 700 rotation period of asteroid. And you find that none of them have rotation period shorter than 2 hours. he thinks this 2-hour spin rate limit is because of the rubble-pile. So he put 2 hours here and then get the bulk density of this group of asteroids, and it turned out to be 3 grams per cc. So this is the bulk density from the rotation period, and interestingly, that is very comparable to the other method, what we have from the other method, like a binary system or from the space mission. And 6 years later, Peter Breivik took a step forward. He got more rotation period of asteroid, and even the asteroid which is as smaller as 100 meters. And he find that the asteroid seems to divide it into 2 groups. The smaller one, they can rotate very fast, even in the minute scale. But for this group, it seems all of them just below 2 hours. So he decided to draw a line here and separate them into rubble-pile and monoliths. As I told you, rubble-pile, the structure is very weak, so they cannot rotate fast. So in this region, you don't find anything faster than 2 hours. But as a single rock, you can rotate as fast as you can. I am not sure if you can have the centrifugal force that eventually can break down the mechanical structure. So he said that asteroids larger than 150 meters, they are in the rubble-pile structure region, and they cannot rotate shorter than 2 hours. But smaller one, because they are monoliths, so they can rotate as fast as they want. And as you see, there is a peculiar dot here. It also found by Peter Breivik, but at that moment he just said that, oh, this is just an exception, so we just leave it over here. However, Canis Hosato theorists have different idea. Say, hey, why the rubble-pile structure can only have gravity? Can we have other forces to survive this object and that it look not unwanted? So he started to think maybe cohesion is a good choice, because we see regoliths on the surface of asteroid, and regoliths do have cohesion, and we believe inside the asteroid also have regoliths. So it eventually will give you another additional force, which is cohesion, to survive OE84. So this dashed line is the new spin rate limit when you add cohesion into the model. And in this way, OE84 can safe and sound stay in here. So sounds like everybody happy. But the problem is, if cohesion is a good solution for the asteroid structure, why this triangular region is so empty? Okay, so we would like to know if there are other superfast rotator in here to find the superfast rotator. For PTF, we focus on finding other superfast rotator because it only has R band and we don't have color. And for the Pan-star one, we can find more superfast rotator with color, which means that we can know what is the composition for each superfast rotator. So here is the result from IPTF. So using several surveys, several high-cadence observations, we found 3 other superfast rotator, which is highlighted with the light blue square. As you see, they all in the rubble-pile region and has a rotation period shorter than 2 hours. And at that moment, we found that the known superfast rotator, their spectral type seems to be tend to have stronger spectral type, like S or metal type or Vesta type, which is like rock. So we just wonder if only the strong material can have superfast rotator. So we decide to use Penn*1 to find more superfast rotator and try to get their color simultaneously. So here is the result from Penn*1. At that moment, we only focus on the known asteroid because we don't have a pipeline to find out the unknown one. So I will tell you the new discovered asteroid later. So from the known asteroid, we find 7 other new superfast rotator, which is highlighted in the red symbol. And here is the list. And when we try to see their colors, so the blue symbols are the new superfast rotator, and the x-axis and y-axis is the SDSS color for asteroid. And we can divide the asteroid into C group, S group, and B group. So as you see, these 7 superfast rotator, they have diverse color, which means that superfast rotator can generate from different material. So at this point, we feel that superfast rotator is very much like the ordinary or average asteroid, except they can spinning very fast. And yeah. Maybe you think the talk is too boring. Anyway, okay, so after deal with the known asteroid, we start to dig out the new asteroid, and we have a pipeline to find the asteroid, which is between 21.5 and 22.5, and there are 300. There are 3,000 new asteroids we found, but because they are very fast, so we only got 120 rotation period. And from the 120 rotation period, we got 13 new superfast rotator. As you see, it pop up in this triangular empty region. Okay. And from the study from IPDF, PS1 known, and PS1 new asteroid, we feel that when the asteroid is getting smaller, it's easier to find superfast rotator. So let me make a short conclusion here. From Penn* and the PTL, we found superfast rotator do exist, and they have diverse color, which means there is no material tendency, and smaller asteroids seem to have more superfast rotator. However, it's still very difficult to find an asteroid has a rotation period shorter than 2 hours when compared to average asteroid. So it looks like we hit a dead end, but we just wonder if what else we can do more. The same diagram, right? Diameter, period, and all the asteroid seems staying nicely under this cohesion limit line. Is there any superfast rotator in this region? If there is, what they can provide us? If there a superfast rotator here, it requires an extremely large cohesion to survive them. Then we want to ask the theorist that what kind of material can generate this kind of large cohesion. And luckily, the PTF upgrade with a huge detector, this one. the most large field of view telescope on the Earth so far. It has a 77 square degree field of view, so it can help us to find anything here. So I did several high cadence surveys, and here are the superfast rotator I found from ZTF. As you see, their 4-day life curve is very beautiful. So there is no need to do the follow-up to confirm their rotation period. So when I plot them onto the diameter and period diagram again, the green symbol is the new superfast rotator from ZTF. And you see, we start to find something over here, not here. We are still trying. So for example, these 3 superfast rotators, they request a cohesion up to thousands of Pascal. So which equal to like a clay on the Earth. So we start to wondering, is there any clay in the space, or or any asteroids made by clay? So can we get that material? So we hope the theorists can come up with a good idea to answer us. And the other thing is that we start to wonder if Jupiter Trojan or Hilda also share rubble-pile structure. If they have rubble-pile structure, they also have their own spin radius. For the current understanding, the bulk density of Jupiter Trojan is 0.5 grams cc, which is corresponding to 5-hour spin rate limit. So here is the diameter period diagram again, and the dot is Mandel, and the red is Jupiter Trojan, blue is Hilda. It looks like Jupiter Trojan, all the Jupiter Trojan are on the 5-hour line. However, some Hilda is faster than 5 hours. So is it possible that Jupiter Trojan and Hilda have different spin rate limit? Or is there any Jupiter Trojan can rotate as fast as Hilda? So in order to measure Hilda and Jupiter Trojan rotation period, we need a telescope which it has very large aperture and also a good field of view, a detector with good field of view. So that is the reason why we proposed to Subaru to use the hyperspring cam, and we initiate a project called Fossil, the formation of the outer solar system and ice legacy. We have 2 major scientific goals. The first one is to identify the spin rate limit of Jupiter Trojan and Hilda. And the second one, we try to determine the population of and the color of tear nodes in different dynamical classes, because this helps us to understand the early stage of solar system. And we are now in phase 1, and in 2020, we got 9 in total. However, at that moment, I wrote this slide. I put a sentence here: pray for good weather. But that is just not enough, because we lost 3 lines in May because of the pandemic. Okay, so, and in the B semester, originally we request observation in September, but due to some human reason, we were forced to divide our observation into August and October. So please, next time, if you were in a tech team and review a solar system proposal where we put some specific period of time or date that we want, we have a special reason. So do not try to change our schedule. Otherwise, it will cause us much trouble, and we might not even can achieve our original goal. But anyway, we still got some data set to work on. So here is the fossil member, which does not mean we are old. Fossil is ancient rock, but as you see, we are still young. Okay, so we have members from Taiwan, from China, from Japan, and also from Canada, and which is a huge cooperation between different institutes. As I said, because we do some observation with very deep limiting magnitude, so we expect most of the asteroids in our observation are unknown, which means that we need to find them first. So we develop a pipeline, and I'm going to, in the following few slides, I'm going to show you how we do that. So if you try to stack the detection of asteroid from the observation within a line, their detection will eventually line up as a line, and the color means they are in the different epoch. Okay, so in this way, we can try to identify them. So let me show you the animation. If I try to stack all the detection from different exposure which are taken within a line, you will start to see the detection of an asteroid start to line up. So all we have to do is that we need an algorithm to find this lineup detection. So the very simple algorithm is to hire a lot of cheap labor, like undergraduate, and you can give each of them a chip of the Subaru hyperscreen camera, and let them try to identify the lineup detection. However, there are 100-something chips, so you probably need more than 10 students to do that. So it's not a good way, and it's not that interesting. So don't do that to your student. Eventually, you will get none. So we finally use the algorithm called Hopf transfer. It just tried to do some mathematical to correlate the detections that it belong to the same line. But I won't tell you detail on this. So here I just want to show you the result. This is all the detection for one night, for one field, before apply the Hopf transfer and after. So we clean up all the detection we don't want and only keep the detection for asteroids. So in this way, we can dig out the asteroid we want. So from the fossil observation, we obtain more than 10,000 new asteroids, which is repeatedly observed in different nights. So here is the number. And there is a light gray, which means we also have other 10,000 asteroids which only observed in a single field. So in total, we probably end up with 20,000 new asteroids. And this diagram just shows you the moving rate and the count of the asteroid we find. So we got TNOs. They are moving very slow because they are further away from us. And then we got Jupiter Trojan here, and Hilda, and then a huge group of Membel and some near-Earth asteroids. So with the light curve we obtain, here is the preliminary result for the rotation period for Jupiter Trojan and Hilda. So this diagram just shows you the diameter and period again. And the blue one is the known Jupiter Trojan with rotation period. And the red one, pink one, is the known Hilda with the rotation period. And with the update of new result, we have new Jupiter Trojan with rotation period in dark blue, and also new Hilda in red. And you see, we seems to break through the 5-hour spin rate limit, and look like the Hilda and Jupiter Trojan, they have similar spin rate limit, like at 3 hours here. So this is the preliminary result for Jupiter Trojan and Hilda. And how about TNO? Because they are very fast, so we only end up like less than 10 good rotation period. But there are 2 rotation period, which is very interesting, because this one, it only has 1.7 hours. The average one is 8.5, and the other one is 4.5 hours. So it looks like TNO shouldn't rotate such fast. So we are proposing for the CFHT DD time to do the follow-up to confirm these 2 rotation period. If the period is true, then we might start to think about why this TNO, which has a size around 100 kilometer, we start to wonder how a big asteroid can rotate so fast. What is the mechanism? Was it born in this way, or there are some mechanism we don't know that can make it spin so fast? So stay tuned. So here I give you the summary. Using different wide field facility, we collect a lot of rotation period, and we contribute more than 2/3 of the available rotation period in the database. And we learn some superfast rotator, which cannot be explained by rubble-pile, and it seems smaller asteroids have more superfast rotator. And the cohesion to survive this superfast rotator can up to 1,000 of Pascal. So, which means we need something like clay in the space. However, it's still very hard to find superfast rotator. It's kind of suggesting that to our spin rate limit is still over there. And we are trying to find superfast rotator which have a diameter up to a few kilometers, and we define them. This can help to constrain the up limit of the cohesion that need to survive superfast rotator. And using the fossil project, we found many Jupiter Trojan, Hilda, TNO, and much more Main-Belt asteroid. And we found 4 Jupiter Trojan which has rotation period shorter than 5 hours. Rotation period shorter than 5 hours is still hard to find for Jupiter Trojan. And if there is no 5-hour spin rate limit, then probably Jupiter Trojan have similar spin rate limit with Hilda. And we do found 2 TNO which look like spin very fast, and we are waiting for follow-up to confirm their period. That will be it. Thank you.